Bones and DNA from Spain are shaking up the out-of-Africa theory. Instead of a unidirectional out-of-Africa model, a multi-directional shuttle dispersal model is more likely to explain the complex phylogenetic connections among African and Eurasian human species. In recent years, a tidal wave of discoveries from deep caves and forgotten shelves across Eurasia has begun to upend some of the most deeply held assumptions about our origins. For more than half a century, the prevailing narrative held that Africa was the place where all major branches of the genus Homo diverged. Anatomically modern humans, Homo sapiens, arose there, and the split between our lineage, Neanderthals, and other archaic cousins took place on the African continent before various groups migrated outward. Yet new fossils and ancient DNA are revealing a far more complex story, one in which the roots of the human family tree stretches deep into Eurasia as well. One of the most astonishing revelations is that the enigmatic group known as Homo longi, popularly associated with the dragon man fossil from northeastern China, now appears to include Homo antecessor, a species represented by 850,000-year-old bones found in the Atapuerca region of Spain. If true, the geographic span of members of this clade stretches across the full width of the Old World, implying that this group could have emerged outside Africa. The researchers responsible estimate that our own clade arose roughly 1 million years ago, while the Homo longi group dates back even earlier, around 1.2 million years, suggesting that the branching events leading to Neanderthals, Denisovans, and modern humans happened in Eurasia rather than Africa. The paleoanthropologist Chris Stringer of the Natural History Museum in London, long associated with Out of Africa, told IFL Science that although most researchers assumed Africa was the cradle of all these divergences, the new data force an uncomfortable question. With the oldest members of the Homo longi clade, Homo antecessor in Spain, and the similarly ancient Yongxian fossils in China, positioned in Eurasia, and with the Neanderthal lineage branching even earlier, Stringer notes that it raises the issue of, did the common ancestor of all those clades live outside of Africa? This possibility lands like a thunderclap across paleoanthropology. Although Stringer still acknowledges that Homo sapiens probably emerged in Africa, the new genetic and fossil evidence allows for the possibility that our species descended from hominins, who first diverged in Eurasia and then subsequently re-entered Africa. However, under the phylogenetic tree released with the study, Homo antecessor lies close to the ancestor of Denisovans, suggesting a confusing scenario. This raises the possibility that the last common ancestor of Neanderthals, Denisovans, and sapiens did not emerge in Africa. Genetic evidence suggests this ancestor lived around 800,000 years ago, leading researchers including Stringer to argue that forms like Homo heidelbergensis or rhodesiensis is too young to occupy that position. Homo rhodesiensis, represented by the Kabwe skull, was a young male who had a primitive-looking face with huge brow ridges over the eyes. If the oldest fossils consistent with our clade are in Spain and China, then the assumption that Africa birthed the major splits must be re-examined, Stringer observed. Whether this ancestor lived in Asia, Europe, or Africa remains uncertain, he has stated several times. What is certain is that during this period, roughly 500,000 years ago, Eurasia hosted multiple hominin species existing simultaneously. Their relationships are only beginning to be understood. In fact, one of the most jarring discoveries fueling this debate began with bone fragments found in the now famous Sima de los Huesos cave, literally the pit of bones, in northern Spain. Hundreds of thousands of years old, the fossils come from at least 28 individuals, preserved beneath layers of sediments, deep in a limestone cavern where temperature and humidity held remarkably steady through the ages. Geneticists extracted mitochondrial DNA from a thigh bone dubbed femur 13, producing the oldest human DNA ever sequenced at the time. Their findings suggested that the individual shared a closer maternal ancestor with Siberian Denisovans than with European Neanderthals, even though the bones show many Neanderthal-like skeletal traits. What's more, nuclear DNA shows they are ancestral to Neanderthals, suggesting a hybrid individual. The anatomical assessment of some femora hinted that at least one of the large limbs belonged to a very robust 167 centimetre tall female with a body mass of up to 88 kilos, or about 5 foot 5 inches and 194 pounds. This suggests that large female body size was common among archaic humans, well adapted for life in cold European Pleistocene environments. Denisovans are also known for robust skeletons, including their womenfolk. Using new techniques, researchers dated the fossils to 400,000 years old, placing them near the era when the Neanderthal-Denisovan split began. Yet the mitochondrial DNA lineage from Sima aligned not with Neanderthals but with Denisovans, creating a paradox. How did a population displaying Neanderthal-derived skeletal features end up with Denisovan genetic signatures? Svante Pääbo, who led some of the efforts, described the results as astonishing, noting that we can now study DNA from human ancestors that are hundreds of thousands of years old. But the implications go beyond technique. If the Sima hominins are indeed related to the population ancestral to both Neanderthals and Denisovans, the structure of the archaic human family tree becomes murkier. It implies that ancient interbreeding, or perhaps indicate that the maternal branches diverged earlier and persisted independently. Another possibility is that external gene flow from another unknown archaic species introduced Denisovan-like mitochondrial DNA into the Sima population. Either way, these findings suggest Eurasia hosted a dense and diverse mixture of hominin populations far more dynamic than once believed. To understand this complexity, it helps to revisit the Sima cave itself. The site has yielded more Middle Pleistocene fossils than any other in the world. The bones, nearly all belonging to hominins, appear to have accumulated through mysterious means, perhaps deliberate deposition, perhaps catastrophic death. The skull and skeletal pieces show a mosaic of archaic and Neanderthal-like traits. At first, paleoanthropologists classified the Sima hominins as Homo heidelbergensis, a presumed European ancestor of Neanderthals. But the mitochondrial DNA results upset this clean story. If their maternal DNA aligns more closely with Denisovans, who occupied regions from Siberia to Southeast Asia, several explanations arise. The Sima hominins represent an early population near the base of the Neanderthal-Denisovan family tree, retaining traits destined to be expressed differently in each lineage. Alternatively, they could reflect gene flow between different archaic groups. As Chris Stringer suggests, perhaps interactions, sexual or otherwise, between early hominins brought Denisovan-like mitochondrial DNA into Western Europe or vice versa, complicating the simple East-West narratives. Mitochondrial DNA only proves there was a Denisovan-like maternal ancestor on the family tree, but 99% of the rest of the ancestors could have been something else. Among the most intriguing species is the aforementioned Homo antecessor, discovered at the Grandolina site in the Atapuerca Mountains. More than 80 fossil fragments belonging to at least 6 individuals, including cranial and post-cranial elements, date to roughly 780,000 years ago. From the outset, paleoanthropologists were struck by the unique combination of physical features. Some aspects, particularly the face, appeared surprisingly modern, with a flatness and cheekbone structure reminiscent of contemporary Homo sapiens rather than Neanderthals or earlier species. Indeed, some researchers argued that the face of Homo antecessor might better reflect the ancestral form from which modern humans derived, with Neanderthals later diverging and developing their distinctive mid-facial projection, massive brow ridges, and robust jaws. This species designation, however, remains controversial. Some scholars argue the fossils represent a very early and morphologically variable European population of Homo heidelbergensis rather than a distinct species. Others believe that the mix of features, spanning the cranium, teeth and mandible, places Homo antecessor closer to the last common ancestor of Homo sapiens, Neanderthals and Denisovans. Some dental and cranial hints even suggest descent from Homo ergaster, the African species that migrated into Eurasia early in the Pleistocene? If so, Homo antecessor might tell us not just about evolutionary timing, but about ancient population movements spanning continents. An intriguing parallel emerges when comparing an 800,000-year-old Homo antecessor skull to that of Turkana Boy, a young Homo ergaster who lived some 1.5 million years ago in East Africa. The similarities hint at deep shared roots. Turkana Boy's skeleton, one of the most complete early Homo specimens ever found, reveals a tall, slender body designed for long-distance walking on open savanna. His brain volume, roughly 880 cubic centimeters at death, and perhaps 950 cubic centimeters in adulthood, was significantly larger than earlier hominins. His brain was only slightly smaller than the 1,000 cubic centimeters estimated for a Homo antecessor skull, also from a 10-year-old. Moreover, the internal structure of his skull shows asymmetry associated with what would later become human language capabilities. These anatomical hints suggest that the neurological foundations of speech and motor planning were emerging during this period. Combined with evidence for progressively more complex tools, they point toward a species undergoing profound cognitive and social transformations. Throughout the long history of Homo erectus or Homo ergaster, cranial capacity continued to increase. Later representatives often reached volumes exceeding 1,000 cubic centimeters, within the lower range of modern humans. This gradual enlargement reflects strong evolutionary pressures favoring intelligence, cooperation, and adaptability. Recent analyses of ancient skulls from Africa and Asia have illuminated another crucial dimension of the story, the evolution of the brain. Homo antecessor and its contemporaries still possessed brains, not unlike those of their ancestors, lacking the full reorganization seen in later humans. Modern human-like brains, both in size and internal structure, appear to have evolved roughly 1.7 million years ago. Shortly afterward, new populations spread across Southeast Asia, carrying with them increasingly complex stone tool technologies and perhaps early symbolic capacities. The fossil record from Java confirms their success, showing how they thrived in diverse environments. Even so, earlier humans with more primitive brains persisted in Eurasia long after these later waves arrived. Encounters between such groups, genetically, culturally, and socially, was frequent. How these engagements played out is still not known, but the archaeological record suggests coexistence, replacement, and hybridization, all contributing to the mosaic of human ancestry. Turkana Boy's lineage could have contributed to the populations that later gave rise to Homo antecessor and eventually to modern humans. The connections remain uncertain, but the anatomical echoes continue to call across the millennia. Taken together, the evidence paints a picture far more complicated than traditional out of Africa, or into Eurasia, if you prefer that term, suggests. Early forms of humans dispersed across the Old World repeatedly, long before the emergence of Homo sapiens. These groups diverged, remerged, exchanged genes, and adapted to unfamiliar landscapes. Some evolved archaic traits, others retained more generalized features. The story is not one of a single birthplace, but rather of webs of population interactions from Africa to Europe to Asia across hundreds of thousands of years. The common ancestor of Neanderthals, Denisovans, and modern humans lived deep within Eurasia. Later populations likely re-entered Africa. Hybrids would have carried their traits onward, forming new lineages. The archaeological and genetic clues from sites like Atapuerca and Sima de los Huesos are still only fragments, haunting, provocative, incomplete. Yet every new find adds more detail to the puzzle. As technology allows deeper analysis of ancient DNA, and as new fossils emerge from long-lost bones in museum drawers and cave pits, our understanding of the past grows richer and more strange. What is clear is that humanity's origins do not trace a straight line. They follow a tangled, branching path through the dark forests, mountains and plains of an ancient world crowded with many kinds of humans. And Spain, once thought peripheral to early human evolution, now stands at its very center. Thanks for watching.